Okay, what questions does anybody want to lead off with? Some questions about anything we've learned so far? Let's see, we had a good discussion last time about just a minute. Occasionally my computer does a thing where it ramps way up and uses all the CPU because it thinks it's overheating, and then I can't do anything. So hold on, let me fix that. Okay. All right, so last time we were talking, was there a question, a comment?
This is Eric. I do still have some questions about that geometric representation, but
yeah, that's exactly what I was going to dive into. So let me put some diagrams up that you can speak to. Oh man, that's bad. How do you like my straight line?
They really should have a straight line tool and circle tool and stuff like that.
I know, seriously. Okay, let me try that all over again.
Are you drawing with your mouse, or do you have a pen and pad?
I have a nice, if you've ever used a Wacom tablet, it's a nice tablet. It's about the size of a sheet of paper, maybe 12 by 8.
Okay.
That's just me. You're like, oh boy, so you are bad.
Oh, there's a much straighter line.
Because these tablets are supposed to be good. You know, artists actually use them to illustrate. I'm just, just a bad dropper.
Mine would be worse. So.
Okay, so we've got this mapping. And I actually I like going through this again, because for me, there's a lot of interesting subtle points here. So it's nice to just kind of think about this deeply for a moment. Yeah, so, okay, let's say now we have some elements, let's say. That's 1, 2, 3, 4. 1, 2, 4. Let's go ahead and put a C1 quadratic B-spline basis on here. All right, now let's draw a CAD domain. Maybe the CAD domain, something like this. And then we can imagine that there's some mapping that is bringing in our parametric CAD domain, but we're going to leave this guy unspecified. Okay, now we were looking at an integral that had everything, kind of all the pieces that we might want to talk about. So we had this integral here. Where we've got indicator function. And then we had N A F hat, comma X E A, and B F hat. We have this D X F, DXC, DXC. So this is the strain energy. Basically, it's the virtual work done by the strain energy with respect to two of the basis functions. Our basis functions are down here. These are our flex guys. These are our elements. And so we map an element into an element. Okay, so Eric, why don't you ask some questions to get us going here?
Okay, so when we're talking about XF, it's understood that it's capturing that domain space that's XC, which we don't really have specified. But at the same time, that domain that's right there, it is it's hard to visualize in 1D when the problem really resides in a 2D plus kind of domain. 1D
Yeah,
is fairly simplistic.
Should we create a little mock-up in 2D?
Yeah, maybe just do like a half arc or something like that. Something that's not complicated, but it has specific geometry.
Okay, let's say, let me. So our CAD is, okay, so let's say we've got, maybe we just make it a circle. So this is our CAD domain here. Okay, so this is omega C. Okay, then let's say that we've got some other geometry that we've created. At this point, it can really be anything you want. Maybe it comes in and matches the boundary for a little while and then it goes away. Let's call that our omega F. Okay. Now, would you like me to create the rest of the paraphernalia, Eric, for this?
So yeah, you can start creating those
Okay, so
annotations on there.
what we're going to assume is that there's some parametric domain. Maybe it's a square. This is going to be our omega hat F. And there's a map that's going to take, let's even put these lines. So there's 3 vertical lines. Maybe it looks like, so maybe those are the 3 vertical lines, and then we've got 3 horizontal lines that come through like that. Okay. And then this is our mapping. And then this is written. So you can see that obviously a linear polynomial wouldn't cut it, right? You can't capture a geometry or this blobby thing with just a linear. So then we pick some nodes, let's say, and now we can draw these nodes, Eric, and that might help a little bit. So let's say that this, maybe it's let's say it's biquadratic C1, so P equals 2 C1. So then how many functions do we have? 1, 2, 3, 4, 5, 6, I believe. So it'll be 6 functions in this direction. Let's give this the coordinate xc. Maybe in this direction it's eta. Those are our coordinates. So there's 36 functions. So there's going to be 36. So we have to pick 36 nodes. Now these nodes, what space do they live in? Let's say this is an XY space, XY. So these nodes here, these XAFs, are they in the xc eta coordinate system, or are they written in the XY coordinate system?
Aren't they written in the CADA? Because they're
Actually, they're not, because this is the information that defines the position in XY space. So these nodes, they live up here. So let's see, 1, 3. I mean, I don't know exactly where to put them, but you can put them anywhere you want, I guess. So there's going to be, 6 rows of 6, basically defining this geometry. Picture's worth 1,000 words, isn't it? Let's see. Well, some people's pictures are worth 1,000 words.
I know mine are worth about 20.
Okay, that's 1, 2, 3, 4. And this is not obviously meant to be representative of anything real here. I'm just. Okay, so these are the x's. So maybe this is x. Maybe this is x1 f here, and then x2 f, and so on, right? So you take these points that are, so this is R2, right? So the nodes, they're part of your mesh, right? So they live in the physical domain. So they're in R2, they're at XY coordinates, and then in some sense, the NAs are just scaling factors. They're saying, how do I take a linear combination of these dots to generate the points on the surface?
Okay,
Right?
so now that we have a pretty good context, my question is, when we have these XFs, we have these points in there, we have the scaling functions. When we're going to basically define that circle using these combinations of our X sub AFs and our weighting functions, if we just throw numbers out there, they're random, then they're not going to make up that circle. So we want to make sure that this really does capture our XC. Now, we don't have XC fully specified, but we do know that we want the XAF and the NA to capture what is in red, the circle there. So my problem is that if you're not solving for XANA and what it should be in order to capture that geometry, how can you be sure that you're actually capturing it?
Well, let's take this integral and actually break it down into what we compute, so then we can talk about that. So let's break this down. So, so this becomes a quadrature rule, okay? And notice that this is over the parametric flex domain. So let's turn that into a quadrature rule. Okay, so let's say we have I quadrature, we have like, I don't know, maybe N sub Q quadrature points defined over this region. So there's a whole bunch of points defined over here. We're going to sum over them, and then we're going to evaluate the indicator function at x of xc sub I, where xc sub I is one of the quadrature points. And then we're going to evaluate our basis function. X. We have these constant material geometry parameters. And then we have our times the weight. Okay, so that's actually what we evaluate. So let's just go through what this means. Okay, so we take a point. Let's say we're on a point here. We take this point, we map it through this guy into this black surface. And then we ask the question through the indicator function, am I inside the cat or outside? Okay, so let's say that we take a point here, maybe, and it maps maybe to like right here. Okay. So if that's your point, then the answer is yes, right? So then this evaluates to a 1, and then we have to evaluate the rest of the interval. So now what we're going to do is we're going to evaluate what these basis functions, but only over, now we know we're inside the geometry. So we're going to evaluate these basis functions inside the geometry, which is the same thing we do with standard finite elements, right? We construct a geometry and a basis over that geometry, and we evaluate the basis. Same thing, these basis functions, right? They're supported inside the geometry and outside, but we don't care about what happens outside. So we're just going to evaluate them on the inside. And then this change of coordinates function really, so it's kind of like saying that we're representing a circle. Maybe we can even take this and let's do a little blow up here. So we have our circle. We don't know, like if I was to say, take a scribe and scribe the isoparameter lines on the circle, we actually couldn't do it, right? Well, this is a good way to describe that. Okay, let's make sure we're clear on this. When I say an isoparameter line, can somebody define for me what that means?
You just fix one of your coordinates in parametric space.
Yeah, so you fix one of the coordinates in the parametric space and see what happens when that line is mapped into physical space. Can we sketch any isoparameter lines onto this circle?
If we know the parameterization.
And do we?
Yeah.
We don't. Yeah, we don't know it. So I have a circle in physical space, but I couldn't, for example, do this. I don't know what the isoparameter lines are because I don't even know what the parametric domain was that defined the circle. I don't know what kind of a function mapped the parametric domain into the circle. So I can't scribe any isoparameter lines through, yeah, this is a good way to describe this. Okay. So we have this, x sub c. I don't know this guy, so I can't put any mesh lines on this because I don't know what the isoparameter domain was. Okay, now let's take a look at what we're doing over here. Okay, let's look at what happens with x sub f. Okay, I do know x sub f. So x sub f is coming in here, and it's taking this black thing and mapping it onto the circle. So let's draw these black lines. Let's see if I can recreate. Let's take this line, kind of looks like this. And then what do we have? We have another one up here that's kind of a funky looking one that goes like that. And then we've got that and that. Okay, and that what that's doing is it's taking this square and we're chopping out some piece of it, right? That has constant, see this one has a constant, this is a good description. Ryan, this must be making you feel good inside. This is like your PhD dissertation.
Yeah.
I keep losing the window here. Or maybe you don't feel good because it's your PhD dissertation. That's a possibility too.
Bringing back bad memories, right?
Okay, I gotta make this window bigger, but it's Zoom's not. There we go. Okay. Okay, so This circle is this blobby thing in the flex domain. And then when we map that through, we get this parametrization of the circle. So do you see how what we've done is we've basically glued an independent parametrization onto the circle in physical coordinates through x sub f.
Yes.
So when I do NA comma x or dx dxc, this dx dxc now is with respect to the parametrization expressed through the black lines on the circle. So that's the geometry. That's how this works, is you don't know the parametrization of the circle that was created by the CAD user. So you create some larger object that has a well-defined parametrization that you control, and then you essentially just paste it onto the physical domain. So that's what this, and then what this integral does is basically what it's doing is it's saying, I'm gonna, then there's like, let's say there's some, let me zoom this. I really like this. So is Chris Wetton on?
Yeah, I am. What do you need?
I want this to be an example in the notes eventually, because this is a nice way to describe what's going on. So am I just entertaining myself, or is this useful to anybody else?
This is useful. I do have a question coming up, so I'm gonna wait for just a moment for you to get this back on there, but then I have a question.
This is the hard part. Draw a circle on there that's consistent.
I know. I was just thinking, okay, I know there's a corner here. That corresponds to this point. Okay. And then it looks like it kind of chops off that there. Maybe comes up, chops off that corner. And comes across pretty straight there. Something like that.
Nicely done.
Yeah.
Yeah, that's pretty good.
Yeah, good. Okay, so now when we put quadrature points in there, let's say we have some quadrature scheme. Maybe let's do like a 2-point scheme where we go like 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, 2, 3, 4, 1, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. Okay, so now you can see we've got basically 1 point here, and then a couple of points in here. And then we've got a couple of points up in here, 1 point here, 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 here. Okay, so that's the points, Eric, where, see, we've evaluated the indicator function. It's evaluated to 1. So we're inside the domain in physical coordinates. And then we resort to the parametrization that we've overlaid on the circle for the rest of the integral. And that's what we do here in this guy. Okay, any questions?
So when you have this mapping, where the main point that I'm getting hung up is on the benefits of doing this over the benefits of doing your basic, the traditional finite element where it's constrained to the body. And when we're talking about like when we're making that mesh, so for example, you're meshing this, you don't, even if you never did have XC, I mean, you have some general representation of XC, and you're creating your XF in traditional FEA sense, right? You're going to be creating a mapping. It's going to look somewhat like this, and you're going to have control points that are inside the domain rather than having some that are outside the domain. But you're going to have nodes that are along the outside of this circle. And if we had the amount of points that we have here, like let's just say you only have the 1, 2, 3, 4, 5, 6, 7 points that are actually touching the outside of the surface. I mean, actually, you probably couldn't fit a mesh with only 7 points, but either way, that's regardless of the point. But you put that mesh on here, you're going to be linearly approximating the edge of that circle. And so if you're trying to figure out an effect,
These are quadrature points, not nodes, by the way.
right? No, yeah, I know, I understand that. Yeah, but there would be quadrature points inside a mesh if you built a mesh on here with traditional FEA that doesn't have nodes or integration points outside of the space. But when you have the nodes that are on there, you're still going to be linearly representing that circle from one point to the other. And the integration
Why is that? Can you help me understand why you came to that conclusion?
Well, so like when you put, if you put a traditional mesh on this thing, right, you're going to have nodes on the surface of this circle. But those nodes, you're always using a linear basis function to connect those two, to map basically the material to this space, this mathematical space of representing it. And so you have, there's part of the material that's not even being represented by the XF, even though it does reside in XC. And so that representation has like, it's not as accurate, but somehow we're saying that this methodology captures that curvature. And so my question is if it's capturing that curvature and it's not a linear representation from one point to the other, but you're not actually solving, you're not solving for XF, or maybe you are, and I'm just missing that step. And where is it at that we actually map where the boundaries are of this thing to XF so that the full curvature is taken into account? You have integration points on the inside here. So like those two integration points are sitting there. We know that those are inside the boundary and we can give them, properties. But how does even this mesh know that you've crossed that boundary and exactly where it happens, unless you were to create integration points that are more refined and you have more of them? So it just seems
for these elements that we call these elements cut elements, or inside, we have outside elements, totally inside elements, which there's one of them, and then we have cut elements. For the cut elements, we do need more quadrature points than I've drawn here, for sure. But the point is look, this boundary right here corresponds to this line in the parametric space. So the question is how do we take, how is this line mapped through this function onto this line? There may be an approximation. Maybe this space down here can't represent an exact circular arc. So even within this space, there will be some approximation. But the point is that this is already what's done in finite elements. In fact, let me draw another picture where I can show you that the situation that you just described is let me show you how the flex method and traditional FEA are the same. Would that be helpful?
If I could jump in real quick here, I think part of the answer, Eric, is that like in either method, you're accumulating error along the boundary. The difference is that in traditional finite elements, you try to control that with mesh resolution, whereas in the flex method here, you're going to control that with the number of quadrature points when you integrate.
Yeah, and the mapping itself, right?
Right.
So if this mapping is fundamentally deficient, that will be an error, or it might be an error just because you don't have enough quadrature points.
I am seeing it now. Okay, thank you. That what you just said made sense.
Mike, can I ask a question
Yep.
about your quadrature?
Sure.
So when you do things like octree refinement to get those shapes in there more accurately, what kind of numerical instabilities does that create?
It doesn't create any, it doesn't make your method unstable. It's just about controlling error, but it doesn't cause the method to blow up or anything like that.
Well, so suppose you have a situation where you're using your quadrature in a way that you want to reduce locking, and now you start doing this refinement. Is that going to affect the locking response?
Yeah, the only way that you become unstable due to quadrature is if you have very few quadrature points. A lot of quadrature points makes you more stable, not less. So if you're looking at locking, what you're going to be doing is reducing the number of quadrature points, and then you can have so few quadrature points that you don't see very much of the functions you're trying to integrate. And then you can get, like, for example, singular stiffness matrices. But in the case where we're trying to capture, for example, this cut cell, and we're adding more points, like maybe we add a whole bunch of points, that's not going to make us unstable.
Yeah, maybe unstable wasn't the right word. I was thinking of locking, for example, where if you have precise integration, you tend to lock, right?
Yeah, so it's a balance. Same in this method. I mean, there will be a balance between how we accomplish the right number of points versus locking.
So is it possible that you have an instance where you have reduced integration so it won't lock, but then you do octree refinement to get a specific geometry, and then it begins to lock because of your refinement?
That's very possible.
So how do you handle that?
Well, we have to come up with schemes that balance those considerations. It's not any different really than how we're doing it now. We just have to you just have to come up with a scheme that balances the number of points versus locking. In this method, though, the way that we're going to handle it actually is not through integration. We're just going to handle it by jacking up the polynomial degree of these spaces. That's the cleanest way to get rid of locking, is just increase the degree, and then you don't have to do anything with quadrature. So that's actually where things are going, I would say, if you look at the literature, is that sure, you can come up with quadrature schemes for locking that are reduced. But the cleanest and most universally applicable is just simply jack up the degree of x sub f. That's the simplest thing to do. And then it becomes quadrature independent.
And then my question resurfaces. So with the quadrature points, I mean, I understand you increase your number of quadrature points, and when you're sampling to find out if it's in the domain or out of the domain, then your indicator function that says this is in the domain, this is out of the domain, you become more and more accurate. But if you up the polynomial degree of xf, and then you're trying to map that surface with that increased polynomial degree, but you never, I mean, I guess maybe my mind is just not understanding the math behind the scenes, and I'm sure that's what it is. But if you're never basically defining that polynomial degree by solving for what it should be and what the coefficients of those polynomials should be based on the curve that you're trying to fit it to, then how do you know what those coefficients should be for your higher order polynomial?
You just pick a degree. You're not like picking the degree to exactly represent the geometry, because you induce an error through quadrature no matter what you do. So you're picking the degree more based on the level of approximation or the accuracy of the approximation that you want to achieve. So like if I had a curvy surface, I would probably just pick quadratic or cubic for everything. and that would be good enough, right?
Mhm. So I guess that when you increase the polynomial degree, yeah, I guess I'm just not seeing how you define those constants in front of the polynomials to
These guys here, the nodes. Are you saying how do we define these,
So
the nodes?
when you up the polynomial degree of your basis functions, don't you need coefficients
Yeah.
defined?
Remember, there's another geometry, right? There's another geometry, the flex geometry out here that we haven't drawn on this picture, right? There's some other geometry out here. There's a bigger geometry.
Right.
Maybe this is a square, right? Or maybe it's a bigger circle or whatever, right?
Mm-hmm.
And this is when you say match the geometry, we're matching the flex geometry. So let me give you a common use case, okay? Like let's say you have a CAD object, okay? It's a square, and let's say there are four bolt holes. Okay, so this is omega C. What we would do is we would come into the, like speaking in terms of like the tools that you would be using, we would come into the CAD tool and we would click on these holes and we would say, remove hole, right? So then all of a sudden you generate a new CAD where the holes are gone. Okay, now that is what we're going to take as our flex domain, let's say in this case. Okay, here's our flex domain. The holes are gone. Now we're going to fit a spline to this geometry. So this, now we're doing exactly what you're talking about, Eric. On the flex domain, on this square, we're going to pick a polynomial degree and we're going to fit a spline to this. So we're going to compute the control points using some fitting algorithm. So maybe we come in here and we compute these points, let's say, if it's linear, so just make it simple, right? So these are our XAFs here, right? So some algorithm, a fitting algorithm, so a CAD fitting algorithm is run. For example, that fits a spline to this new domain defined by the CAD system that we're calling omega F. And the CAD fitting algorithm spits out the control points. Okay. And then what we do is we go ahead and we put the features back into the CAD. Okay, let's put these features now back into the CAD. Okay, now we know that omega C is contained in omega F, so we're in a well-defined situation mathematically for our method, and then we do everything that we've talked about up to this point. So this is how we control we create our flex domain is a piece of CAD, Eric, like in CATIA or SolidWorks, or we create it from, usually we take the actual original CAD, omega C, we do some manipulations to it, and then we generate a new piece of CAD, which we call omega F, and then we fit a spline onto omega F, that creates the control points, and then we reinsert features to create the flex, the whole problem.
And when you insert those features, that fitting algorithm is still fitting.
No, you don't fit. You insert the features back into the CAD. The spline is fit to omega F. So those features are just put back in and the mesh doesn't even know they're there. You only fit to omega F, not omega C.
Then you just use the indicator function
Yeah,
to tell
yep.
if you're inside the.
Yeah, because any BREP, you know, whether you're using any kind of ASIS or Parasolid or whatever, they all have inside-outside tests that you can run. Very robust, very efficient. And so literally the reason this is so different than any other immersed scheme that's ever been proposed is because literally we use a CAD system to create omega F. It's not just a box. I mean, it can be a box because you can create a box in the CAD system, but it can be, I mean, you could have a very complicated object, you know, that has a lot of features. You just suppress those features and then fit a U-spline or another kind of spline to it and then reinsert features.
Mike, just a clarification though, you aren't necessarily using the trimmed B-spline directly, are you? From the CAD system?
Yeah, the BREP, right? The Omega C, the original CAD. The only API call that we make into the CAD kernel is this guy right here, the inside-outside call.
So, but you're not relying on the parameterization of the CAD trimmed B-spline.
Yeah, so yeah, well, yeah, we create a CAD. The CAD representation of omega F is just in physical coordinates. We never use that parameterization.
Right.
We just use it for fitting, right? And the fitting is what then gives us the omega hat F.
Yeah, because so often that CAD parameterization is off anyway for what you want to do.
Yeah, so I guess the steps are, now that I'm verbalizing this, is you have a CAD object in some CAD program. Then you go through a process that creates another CAD object, omega F. Then we approximate this. Let's call this even maybe omega F. What do you guys want to call this? Like it's the omega F in the CAD kernel. So, oh man, maybe we'll call this F bar. Then we do a fitting algorithm to create our real omega F, right? And this approximation doesn't matter because mathematically the only thing we require is that omega C be inside of omega F. And then this, of course, induces automatically our omega hat F. And then we can compute our basis functions and then we can go and do FEA on it. So that's the workflow. So a CAD user is inside of their phase, maybe they're in CATIA and they create omega C. And then without ever leaving their CAD program, they create this omega F hat. And then they use like our software, for example, to create our U-spline approximation to omega F hat. And then once we have omega F, we can just throw this away. We no longer need it. The only requirement is that omega C be inside of omega F. And then we do a CAD fitting operation and then we run the FEA. And then we're also devising term capabilities where you don't have to do CAD fitting. You can actually create the geometry natively in the context of some spline that we can use. But for, you know, in general, you do a fitting operation. So this right here is fitting. And to Eric's question, it's this algorithm that produces these guys. So I don't know if that was helpful to anybody, but that was helpful to me to go through that.
That was very helpful. Thank you very much.
Any other comments? I'd just like to take a little bit of a pulse. I don't know if this was, I can't get a sense for how anybody else is doing, but is this making sense to people?
It was helpful for me.
Thanks, Carl. Okay. Well, good. I'm glad that I was able to at least help 2 people today. Yeah. Great. And so this is really this is the foundation of the method. Is, as I said before, it's this thing right here is really the enabling piece. And so this thing is the enabling piece and its connection to real CAD, right? Like real CAD kernels in the context of what we would call a BREP representation, which is what's inside of the CAD kernels. This is the piece that's missing from every other immerse technique. And it's really the piece that makes it, you know, because you can see it just as a closing point, notice that if you have control over how you create this flex domain, then you have control over how these lines look. Like if everything that if everything was a box, you know, like if all you could do was boxes, then you can get parametrizations that are really not suitable for the underlying object, right? Because you have this like really rigid topological requirement on the isoparameter lines. And so that's, but if you can kind of bend the flex domain to capture the bulk geometric characteristics, then the power of splines really begins to shine, and it kind of covers up any other errors that you might induce in the method. Okay, any other questions before we finish up for the day?
I have a small question.
Okay, yep.
So you're talking about bending the parametric domain. So you started out with a regular grid, like on the lower left-hand side here, but you don't necessarily have to start with a regular grid, right? I mean,
you splines, like in the advanced spline discretizations that we have, they can be completely unstructured. This parametric representation is completely unstructured and it's completely local. And that's why we can capture, that's why we can create like actual complicated flex CAD inside of a CAD kernel and then turn it into splines. Okay. Because it's not structured.
But that's something unique to you splines. So some of these other splines don't have that.
That's exactly right. Yeah, that is one of the, well, that was really the driving kind of emphasis for that technology, was we were trying to get to be able to do this, and we knew this was a missing piece.
Okay, thanks.
Yep. Okay, so Chris and Kaylin, can you guys hang around for a bit? And we will stop our official lecture right now. I'm happy to take any other outside questions for a few minutes if you have any.
Thank you, Dr. Scott.
Yep.
Thank you.